So we'll wait for a couple of minutes and we will start. I'm going to quickly go over the vector formulation for backpropagation, starting from some brief revision of what we did in class and some of the rules for derivatives and such like, and we'll use that to perform actual backpropagation calculus. So do you have any questions from the class? Anybody? Any questions? I'm assuming not, right? Let me see if I can get a list of participants here on the side. Perfect.
I have a question.
Okay.
You plan to have like another like this extra classes in the future?
I only do that when I run out of time. Why is this?
I was asking, is there any other like extra?
Yes, so
Any other extra classes like this that we have to plan advance in the future?
So why? I'm not sure why I'm getting to. Are you hearing echo now? Okay, so I don't plan for it, but sometimes when I run out of time, like I did today, then I may do it. So it does. These are not planned, but they may happen. So today, for example, we had to wait for the early people to come in, and I sort of built that into my schedule for today. This is not planned. It's not something that you expect when the semester begins, but it happened. So accordingly, I just shifted some of my lecture out. That's all. So let me begin, right? We're going to begin a little behind where we left off in class. Now, all of you have sort of seen how the backpropagation algorithm actually worked when we discussed it in terms of the derivatives for individual terms. And in performing backpropagation, there were two steps. What were the two steps? Anybody remember? Someone want to answer? What were the two steps? So there are lots of you guys over here. So I'm going to ask one of you if nobody will answer. Ajinkya, so what were the two steps? Hello? Can anybody hear me?
Yes.
Okay, so what were the two steps?
If I remember right, well, first you'd have to do a forward propagation.
Yes.
Or are you asking two steps in general or two steps
No, that is
specifically
right.
to backprop?
So first we had to do a forward propagation, and then we had to perform the backward propagation, right? And there was a lot of arithmetic involved. And so the equations look fairly complex, but then when you do the same thing in vector notation, in linear algebraic notation, it ends up being much simpler. So how do we do this? Now consider consider any layer of a network. So a layer is going to have many neurons of this kind. Assume this is the kth layer, right? Then the neurons in the kth layer actually get a bunch of affine values going in first. So a z goes in and a y comes out, right? For each one of these. So I'm going to represent the set of z's for the kth layer. This is for the kth layer. I'm going to represent the set of z's as a vector. I call this z subscript k. Again, in this instance, the subscript represents the layer, which is simply going to be z1 through z dk. So dk represents the width of the kth layer. And so also, the set of y's that come out of the kth layer, I'm going to represent that as a vector yk, and the entries of this vector are going to be y1 through ydk. So everyone with me so far?
Yes.
Okay, right. So now when I have a layer, so let's say this is the kth layer, then there's going to be a k minus 1th layer, correct? And so I would have the y's from the kth layer. These are the y's from the k minus 1th layer. They are used to compute the z values in the kth layer, correct? And I'm just showing some of the connections over here. And so you'd first compute the z. So this is this collection of y's. The output of the k minus 1, they are going to be yk minus 1. The z values in the kth layer are going to be zk. And then subsequently, these are put through the activations, and you're going to get the vector yk, right? Now, associated with these connections are weights. And using the scalar notation, wij is the weight from the ith neuron, output of the ith neuron in the k minus 1th layer, to the jth neuron in the kth layer. So everybody remembers this notation, right? Everyone
Yes.
with me? Okay. So now let's look at the z value out here. So if I were to write this equation down, then this is what it's going to be like. It's going to be z. Now this is the scalar. So this I'm not speaking of the vector. I'm speaking of the jth neuron in the kth layer, right? This is going to be summation over I wij of k times yi of k minus 1 plus bj of k. So is this equation okay? Is everybody with me on this equation?
Yes.
Right? So just give me a thumbs up, guys. Raise your hands. I'm going to ask you to do this. And unless I see like for 50 hands raised or whatever, I'm not going to move forward because there are 50, 56 of you. So is everybody with me here? Raise your hands, right? Thank you. So now, so if I wrote all of these guys, these y's in the k minus 1th layer, that's going to be y1 of k minus 1 dot dot y. The superscript is going to be k minus 1. How many terms will I have here? Anyone? How many terms will I have?
T.
It's going to be the number of neurons in the k minus 1th layer, correct? If I wrote it like this, right? Then I can write zj of k equals, I've written the y's in vector format. So this is yk minus 1, obviously. And so this is just a vector notation for this term. Zj is a scalar. So what would I have to multiply this vector by to get the actual value here? Anyone? This is going to be w, 1j of k, then w2j of k, and so on, correct? W dk minus 1j of k. And that's not enough. I also have to add bj of k. So is this making sense?
Yeah.
Raise your hands if this makes sense. This has to, okay, so this is easy, right? Now extending this notation, I can now, so if you look at this guy, if I were to stack, just continue to look at this equation. Suppose I were to stack the z's into a vector, right? So this is z1 of k, z2 of k, and so on, all the way to zdk of k. Then the y's are common for all of these. So this is simply going to be yk minus 1, which is this vector. But now for each z, I have to add the corresponding bias, right? This making sense? And now out here, for the first z, this is the set of incoming weights. to the first neuron, right? So that's going to be W11, W21, WDK minus 1, 1, all with the superscript K, right? Or in general, for the jth entry over here, this is going to be the set of weights going into the jth neuron. Is this making sense to all of you? I'll just wait. I need at least half of you to tell me it makes sense. So, all right. And so this I can write as my matrix WK, which is this matrix of weights to the kth layer. And the matrix of weights to the kth layer actually has this form. It has the jth row of this matrix is the set of neurons to the set of weights to the jth neuron. And so this is the entire set of weights. So I'm going to have as many columns as the number of neurons in the previous layer and as many rows as the number of neurons in this layer, because each row corresponds to one of these neurons and each column corresponds to one of these neurons. And now using this notation, I can now simply write in vector format. Going back here, I just have ZK equals WK times YK plus BK. So is this clear to everybody? Is this clear? I'm just wait for some hands to be raised. Okay.
Y would be K minus 1, right?
Y minus K minus 1. Thank you. Correct. So thanks, Ruchita. You caught me on slides too. So this is good. And so now I can just write ZK equals WK YK minus 1 plus BK. And YK is the activation function applied to ZK, right? And so given this, now I can go back and perform my forward propagation trivially. I'm going to set Y0 to be my input. And then what is the first thing I would compute? Anyone? What is the first thing I would compute from this one? Z1, right? And Z1 is going to be W1 Y0 plus B1, right? What is the next thing I would compute? Like so, Y1 equals F1 of Z1, right? And then next, what would this be? What would the next term be? Z2, right? And then Y2 and Z3 all the way to the end, okay? So this is very easy. Now here's something very interesting. Take a look at the lower equation, right over here. Y1 equals this activation times Z1, right? Y2, but then Z2 is computed using Y1, right? So Y2 is this activation times W2 times Y1 plus B2, right? So as you can see, Y2 is a nested function where these activations operate on an affine function of the outputs of this layer. So do you see how this is nested? Right. So I can keep going forward, and the entire network is just a nested function where you have this activation operating on this affine function of this activation operating on this affine function of this activation. And the innermost variable is going to be the input. Okay. So here's the entire forward pass. I'm going to set Y0 to be the input. And then I scroll through the layers. In each layer, I just compute the affine values, affine vector ZK, which is WK YK minus 1 plus BK. And then I compute the activation, which is YK equals FK times ZK. So this is, as we saw, this is, when I write it in pseudocode, this is extremely simple. There's nothing particularly complicated about this pseudocode, right? So this is where we start. Now, we're going to do we've performed the forward pass. We're going to perform the backward pass. But before performing the backward pass, I'm going to throw some nasty calculus at you. Now, how many of you want to do math and how many of you want to do figures? If you want to do math, raise your hands. Okay, a small number. How about figures? How about if I did it with figures? Raise your hand for that, okay? That seems to be a larger number, okay? So let me do this with figures. Both, all right, let's do it with both. Now, suppose I have a variable x, but this is a vector, right? And it influences a variable y. What was the I can always draw a influence diagram of this kind, right? You guys with me?
Yeah.
Okay. So now suppose I were to write the derivative version of this influence diagram. What's it going to look like? Anyone?
dy by dx.
But these are vectors. So what is it going to look like? Can I pick a name and ask you, Nihar, what would it look like? Is Nihar listening? Hello? So Nihar, I'm waiting for you. You guys are logged on, but you're not listening. Okay. It's going to be delta x. And then this is going to be delta y. These two are vectors. And this is going to be, or these could be, so this is going to be the derivative of y with respect to x, correct? If y is a vector and x is a vector, this is going to be a Jacobian, right? If y is a scalar and this is a vector, what's this going to be? It's going to be a row vector. It's going to be the transpose of the gradient, right? Everyone with me? Right, okay. And suppose I have x going to y going to z, okay? This guy is going to be the derivative of y with respect to x. This guy is going to be the derivative of z with respect to y, right? And now, what is the relationship between the derivative of z and x? I want the derivative of z with respect to x. What is that going to be? Does anybody want to take a guess?
Matrix multiplication or tensor multiplication.
Matrix multiplication, both are matrices, right? So what's it going to be? What rule will we apply over here?
Chain rule.
Chain rule, right? So what are we going to, so when we apply the chain rule, what are we going to be multiplying?
Derivative of y with respect to x multiply with derivative of z with respect to y.
Are you sure it's in that order?
Oh,
Okay. So this is where you have to, scalar versus matrices become different, right? You have delta z, but what is the different relationship between delta z and delta y? Is delta y times the derivative of z with respect to y, correct? Everyone with me? Right? It doesn't matter whether it's a scalar or a vector. This is the general rule. That's what we said, remember? And what is delta y? What's delta y?
that would be derivative y with respect to x multiplied by delta x.
Times delta x, correct? And so when I write this down, I'm going to get delta z equals the derivative of z with respect to y times the derivative of y with respect to x, delta x, right? So now, how did the chain rule work over here? In which order did we multiply the things? Can you multiply them in any odd order?
Reverse.
Reverse. Can you change that order? Would the math work? It would not work, right? So here is the thing. When I draw the influences, you're going to multiply this derivative, but you're going to right multiply the derivatives going forward. Is this clear to everybody? Right? So it makes a lot of sense to begin thinking about which variable influences which variable, right? So here's what I have. First, this we agree. This we are all familiar with. Delta y equals the derivative of y with respect to z times delta z. And so I won't actually go through all of these sizes, but you can check that simply because of the nature of this relationship, the sizes must match. If the sizes don't match, then you have a problem, because it means if you don't multiply things in the right order, the sizes will not match. So please go ahead and take a look at the slides, and it will tell you, right? So for example, if y is a scalar and z is a vector, this gradient is going to, and z is an r component column vector, then this derivative is an r component row vector, right? Its transpose is called the gradient. Now suppose I have a matrix of this kind, the same rule applies. So if this is an m component vector and this is a d component vector, the only way this relationship holds is, what must the size of this derivative be? Anyone? What must the size of this derivative be? It's going to be m and d, right? M cross d, correct? Because you're multiplying the d component thing by an m cross d matrix, otherwise you will not get an m. So this derivative size is going to be an m cross d matrix, which, and here is the interesting thing, this derivative is this matrix, this Jacobian. Observe how y is simply a vertical stacking of components, right? So this Jacobian 2 is going to be a vertical stacking of the derivatives of y with respect to z, and the derivative of these components of y with respect to z. And so you can literally write it out here. If I have y equals y1 through ym equals some function of z1 through zn, then the derivative of y1 is going to be what? The partial derivative of y1 with z1, partial derivative of y1 to zn, right? The derivative of y2 is going to be the partial derivative of y2 with zn all the way to the partial derivative of y2 with zn. Z1, yeah, z1, zn, right? And I can write this for each one of these guys. And so the Jacobian is just this matrix, which is a vertical stacking of the derivatives of the individual components of y. So that's what this equation looks like. It's called the Jacobian. And so here's what it is, right? The Jacobian of y with respect to z, I've just flipped the notation. The y comes in the denominator and the z comes in the argument, because it depends on the position where you're computing the derivative. But then if you look at this Jacobian matrix, it's simply a vertical stacking of the derivatives of each of the components of y with respect to the z vector. Is this making sense to you guys? Right? It's very easy, right? It's easy to remember. Now, and of course, if I have a layer of scalar activations, then in this case, each z only influences the corresponding y. So the Jacobian is simply going to be a diagonal matrix. You have as many y's as z's, and the Jacobian is going to be a diagonal matrix, because perturbing this z has no influence on this y, so the off diagonal elements are going to be 0. Whereas if you have a vector activation, then each z is going to influence every y, and now the Jacobian is going to actually be a full matrix. Okay? But regardless of whether it's a full matrix or a diagonal matrix, this property must hold, the derivative of y equals the Jacobian of y with respect to z times the derivative, delta y equals the Jacobian of y with respect to z times delta z, right? Now, let's consider something of this kind. I have z of I is some function of y, right? So using the same, if I say z equals wy plus b, what is the derivative of z with respect to y? Anyone? It's going to be w, and it's very easy to see why it's going to be w. I have z equals wy plus b, right? So delta z, if I perturb y by delta z is going to be w times delta y. That's it, right? Because the only thing I'm perturbing is y, which tells me that the derivative must be w. You with me? Right. Easy enough, right? So the derivative of y, z with respect to y, is w, okay? What is the derivative of z with respect to b? So here's what happens. If I fix y and perturb b, then the only change in delta z in z is going to be delta b, correct? If I fix y, there's no perturbation in y. Then if I have z plus delta z equals wy plus b plus delta b, right? So which tells me delta z equals delta b, right? Because this was z. And so the derivative is identity. Is this clear to everybody? Right? You can see where it's coming from. It's nothing complicated. You just have to work your way through the basic formulae, all right? And now, suppose I have y equals y of z of x. This is the chain rule, right? Don't look at the slides. Just look at this guy. Can you tell me the derivative of y with respect to x? What's it going to be? What is the influence picture over here? I have y equals, what did we have on the slide? Y of z of x, right? So what is the influence picture over here? What influences what? Anyone? X goes to z, goes to y, right? So what is the derivative of y with respect to x? We'd have to go, which way would we go? In the reverse, right? So this is going to be the derivative of y with respect to z times the derivative of z with respect to x. Because you have to go backwards computing the derivative, right? Everyone with me? We've just gone through this. And it's got to make sense. It's just, there's nothing complicated about this at all. It's very, very simple, right? And this holds regardless of whether x is a vector, z is a vector, or y is a vector. Regardless of what these are, this relationship must hold. So in the special case where x, z, and y are all vectors, the derivative of x, first, the derivative of y with respect to z is going to be a Jacobian, right? And the derivative of z with respect to x is going to be a Jacobian. So you'll be going outwards in is the Jacobian of y with respect to z times the Jacobian of z with respect to x. And if you're ever confused about the order in which these things must happen, you can just write out the influence picture and you will get things right. But then you can also sort of explicitly write things out in this manner, right? You know that delta z equals Jacobian of z with respect to x times delta x, and delta y is the Jacobian of y with respect to z times delta z. Chain them up and you should get this formula, right? So everyone with me? Yeah. Observe that as you go from outside to inside, you're on which side are the derivatives being multiplied? To the right or to the left? as you go from outside in, on which side are the derivatives being multiplied, right or left? Right, because first you got the derivative of y, then you multiply the derivative of z. And this is dependent on us using column vector notation. If I were using row vector notation, what would happen? Everything gets transposed, correct? That's what you use in your Python program. You use row vector notation, everything gets transposed. In that case, what would the order be? It's going to go from right to left. You're going to keep multiplying to the left, right? It would be reversed. Okay, so here's the case where I have a scalar. So you can check out that the sizes work out, right, over here. So here, for example, if I have a scalar function of a vector function of a vector, then the derivative of d with respect to z is going to be a row vector. The derivative of d with respect to y is going to be a row vector. The derivative of y with respect to z is going to be a, what's it going to be? Z and y are matrices, vectors, d is a scalar. So what is the derivative of y with respect to z? Is it a vector or a scalar or a matrix? So here, let's be clear. I have d, this is a scalar, of y, which is a vector, of x, which is a vector. Okay, just to clarify, I put these over bars. So what is the derivative of d with respect to y bar? What is this? This is going to be a row vector, correct? D is a scalar. Y is a vector, right? And what is the derivative of y with respect to z? Y is a vector, and y with respect to x, y is a vector and x is a vector. This is going to be a matrix. It's going to be a Jacobian. And the product of a row vector and a matrix is, what's that? What is the product of a row vector and a matrix? It's going to be a row vector, which is exactly what you get, right? All the sizes will match up. So just remember that, okay? And now, finally, if I have something of this kind, d equals f of z, where z is an affine function, then you can see very easily that the derivative of, where z is an affine function of y, then the derivative of d with respect to y is going to be the derivative of d with respect to z times the derivative of z with respect to y, correct? Going outwards in, which is going to be the derivative of d with respect to z times w. So everybody see how this first equation happens? Right? It's a derivative, I'm going outwards in, correct? So it's the derivative of d with respect to z times the derivative of z with respect to y, which is w. So also the derivative of d with respect to b is going to be the derivative of d with respect to z times the derivative of z with respect to b. And this derivative we've already seen is an identity matrix. So the derivative of d with respect to b is simply going to be the derivative of d with respect to z. Okay. Now there's one final crazy term over here. Okay. And this one, I'm not going to try to explain. The math is not particularly complex, but it's probably not worth our time. But suppose I have an influence diagram of this kind. This is not, I'm not speaking of the derivative influences, the direct influences. So I have some function x, where some variable x, which influences the variable y, right? And specifically, suppose I have a weight w over here. So y equals w times x plus whatever. Suppose I have something of this kind. And let's say y in turn influences some other variable d. Now you're going to have to take this on faith. Then this, let's say these are all vectors and this is a scalar. Then the derivative of d with respect to W is going to be slightly different. And how is that? I can rewrite this like so. If W is the variable that I'm interested in, how is this influence diagram going to change? It's going to be W influencing Y influencing D, correct? And this is a where W influences Y through X. Yeah. And because of this crazy business that W is a matrix, some things change. If I want the derivative of D with respect to Y, W, if I want the derivative of D with respect to W, then that is going to be the input X bar times the derivative of D with respect to Y bar. So this is somewhat inverted. We can show why. I can take that off to Piazza later. But if I have something of this kind, where X, Y is an affine function of X, and D is a scalar function of Y, then the derivative of D with respect to W, where is going to be the input times the derivative of D with respect to Y. And now for this is a simple, so do you guys get that? This, I'm just asking you to believe me. W is a matrix. It doesn't have to be square. X and Y are vectors. So, you know, the matrix is going to make the sizes match up. But then here is the thing. Suppose, regardless of whether it's a matrix or a vector, suppose I have some scalar D, which is some function of some variable. Let me just call this V. Then the derivative of D with respect to V, this is going to have the same size as V transpose. It's always going to be the case. So which is why when V was a column vector, the derivative of D with respect to V was a row vector. If V is a matrix, the derivative of D with respect to V is going to be the same size as the transpose of V. Okay. So if you, so is this making sense? Just as something to memorize, the derivative of a scalar with respect to any term is going to be the same shape as the transpose of that term. That making sense? Well, at least you can memorize it, right? But then if you take this on belief, then you can see how, so suppose I have Y, and then this goes to some Z, and this goes to some D, and there's some W. D is a scalar. Then if I take the derivative of D with respect to W, that must be the same size as the transpose of W. Yes, these calculations can be arrived at by looking at tensor math. I'm just not going to spend time on it. I have a little write-up for it. Okay. So if I do so, right, then we can see how Y. So what is the derivative of D with respect to Z? Suppose this is an n cross 1 vector. This is an m cross 1 vector. Then W is going to be m cross n, correct? Everyone with me? Now, what is the derivative of D with respect to Z? What is the size? What is the size? Come on, folks. Z is m cross 1. What is the size of the derivative of D with respect to Z? 1 cross m, right? And Y is n cross 1, right? So what is this size of this product? This is going to be n cross m, which is the transpose of W, right? The size works out. So again, I want you to remember that in a situation like this one, so in a situation like, where do I have it? This one. the derivative of d with respect to w is going to be the input of this influence times the derivative of d with respect to the output. This is the only thing that I need you to sort of memorize and believe me, okay? And so when I do that, I'm going to get you this derivative of d with respect to w is going to be y times the derivative of d with respect to z. So do you see how this equation happened? So y influences z, which influences d, right? So the derivative of d with respect to w is going to be y times the derivative of d with respect to z. So is this equation making, at least based on what we've seen, is it making sense? Yes, no? Okay. I see very few yeses and very few raised hands. Is it making sense? So what is the doubt here? Questions, anybody? I'm going to jump off the deep edge. I'm just going to take all of this for granted because backprop will be 5 minutes of explanation once you understand this. So is this making sense? Yes or no? I see only one hand raised, so I'll wait for at least a few more. All right, a few hands are raised. So you see these two equations. The derivative of d with respect to this b is simply the derivative of d with respect to z. And the derivative of this d with respect to w is y times the derivative of d with respect to the z. Okay, fine. So how does that apply to a neural network? Suppose I have a layer of this kind. Then I have zk equals w times yk minus 1 plus b, right? That's the equation over here. And zk in turn is going to influence the divergence. And so the derivative of the divergence with respect to yk minus 1 is going to be the derivative of the divergence with respect to zk times wk. So do you guys see how those relationships gave us this formula? I'll wait for more hands to be raised. This was a direct outcome of what we just saw, right? So the direct derivative of the divergence with respect to yk minus 1 is the derivative of the divergence with respect to zk times wk. And what is the derivative of the divergence with respect to wk going to be using the same formula? Anyone want to tell me? So just to clarify, if I can get this whiteboard here. If you look at the influence over here, the influence says yk minus 1 influences zk, influences the divergence, right? So what is the derivative of the divergence with respect to wk going to be? Someone? We've just been through the formula, right? One brave person, so I can continue. Just one brave person. Let's take a look at this slide, previous slide. Over here, what did we have? Take a look at this one. Take a hard look. And now tell me on this slide, what is the derivative of the divergence with respect to wk? Anyone? So can I call up a name? Kevin?
I'm here. I'm just trying to still figure it out.
So how did we say this, right? So over here, I know you guys are all here. I know you guys are trying to figure it out. But then here's what I said, again, just to reiterate. Here's what we saw just now. And I sort of flung this at you. But if I have, like y influencing z, influencing d, this is a vector, this is a vector, this influences through a matrix W, and d is a scalar, then I said that the derivative of d with respect to W had a specific form. What was that?
I believe it was you, in this case, right multiply on this by W, but you take the derivative of d with respect to z. And if I remember right, it was the W went on the right side.
So W, I'm computing the derivative with respect to W, right?
Oh,
So-
sorry. Oh,
so-
y.
Right. So it's going to be y times the derivative of d with respect to z bar, right? This is what I repeatedly said, that if you have a relationship of this kind, it's the input times the derivative of this guy with respect to the output. Right? I just worked out the size and showed you that this is how it worked. Everybody remember? Let's do at least 5 of you remember. I'll wait for 5 hands to be raised. Okay, I've got 5 people, so good enough for me, right? Now, using that same thing over here, what is the derivative of the divergence with respect to WK?
Yk minus 1 times derivative of divergence with respect to zk.
Absolutely, right? That's exactly what it's going to be. Beautiful. So you guys have it, right? This is the formula, in case you didn't see my pen writing it. So is that making sense to everybody? Right? And so we're all set. Beautiful. I'm not even going to spend some time. So over here, the derivative of the divergence with respect to, we just saw the derivative of the divergence with respect to yk. It's the derivative of the divergence with respect to zk times wk. The derivative of the divergence with respect to bk is the same as the derivative of the divergence with respect to zk. And the derivative of the divergence with respect to wk is the derivative of the divergence, or is yk minus 1 times the derivative of the divergence with respect to zk. That's it, right? I'll skip the poll. But then here is the backward pass. You're going to do the forward pass. You compute all the intermediate variables. Eventually, you compute a divergence, and the divergence is going to be a scalar, right? I'm assuming that you know the function formula for the divergence, so you can compute the derivative of the divergence with respect to the output of the network. Now, if the output of the network is a column vector, what is this shape going to be? What's the shape going to be? Come on, guys.
Row vector.
It will be a row vector, right? So then, from here, what is the next term I'm going to compute? The derivative of the divergence with respect to the z over here, right? That's what I'm going to compute, am I not? It's backpropagation, remember? So going back, can someone tell me what the derivative of the divergence with respect to the previous z is going to be? I have z that went into this activation function, which gave me y, and then I got the divergence. I have the derivative of the divergence with respect to y. What is the derivative of the divergence with respect to z? What rule will I apply? Come on, folks.
Multiply by w to the right.
I'm going to multiply which? The derivative of the y with respect to z, and that's going to be to the right, correct? And what kind of derivative is that? Come on, guys. What is this derivative? That's a Jacobian, right? Folks, come on, please, yes. Yeah. And so I just multiply the Jacobian derivative of y with respect to z, going one step back. And so this is going to be the derivative of the divergence with respect to z, is the derivative of the divergence with respect to y, which we already have, times the derivative of y with respect to z, which will be a Jacobian, right? Then I want to, so I already have this, observe, this is a row vector, this is a matrix, so this result is going to be a row vector of the same dimensionality as z. Next, I want to compute the derivative with respect to these weights. How will I do this? Anyone? We've just been through this. How will I compute the derivative with respect to these weights? One person, please tell me.
We'll multiply yk minus one with the, d divergence by dZn.
Yes, so you're going to be multiplying the first. Actually, I've sort of written it in a different order. If I want the derivative of the divergence with respect to y, that's going to be the derivative of the divergence with respect to z times the derivative of z with respect to y. And what was that one? This guy is just the weight matrix, right? The derivative of z with respect to y is just the weight matrix. So if I want the derivative of the divergence with respect to this term, it's the derivative of the divergence with respect to Zn times this weight matrix. So I got back here, but then I can compute the derivative of the divergence with respect to the b term, the bias term, and that's simply going to be the derivative of the divergence with respect to z. And the derivative of the divergence with respect to this weight matrix is going to be the input yn minus 1 times the derivative of the divergence with respect to Zn. So these two formulae are going to give me the derivatives for these parameters, right? You guys with me? I need at least 10 people, 15% of the class to have understood what I'm talking about. Okay. So what is the next thing I'd compute? Someone? What is the next thing I'd compute?
The forward layer.
I'm going to go backward here, right? And that is the derivative of the divergence with respect to these z values is simply going to be the derivative of the divergence with respect to these y values, right, multiplied by the derivative of the y's with respect to z. This derivative is already available. We just have to include this new term. And this new term is simply the Jacobian of these activations, right? Everyone with me? Okay. What is the next thing I'd compute? Someone? What is the next thing I'd compute? I have the derivative of the divergence with respect to this one. Where do I go next?
With respect to weights.
With respect to weights, and what will that be?
Yn minus 2 d divergence Zn minus 1.
Beautiful, right? So actually, the way I've written it, I'm going to compute the derivative with respect to this yn minus 2, which is the derivative of the divergence with respect to Zn minus 1, times the derivative of Zn minus 1 with respect to yn minus 2, which is just the weight matrix. So that gave me the derivatives here. But then I also get the derivatives with respect to the bias terms here, which is simply the derivative for Zn minus 1. And the derivatives for these weights is going to be the y over here times the derivative at Zn minus 1, right? And then I can continue this backward all the way until here, till I compute the derivatives of the divergence here and the derivatives for these weights and biases, right? So here is the complete set of backward propagation rules. You're going to start off with the initial derivative for the divergence with respect to the output of the network, which we assume we can compute because we have the divergence function. And then we're going to go backwards through this network. And first, what we will do is we're going to take one step back and right multiply the derivative for the output of the layer with the Jacobian of the activation. And then you're going to get the derivative for the output of the previous layer by right multiplying this term by the weight matrix. So as you keep going back, at each loop, you keep right multiplying terms. So if you take a look at what's happening through this recursion, first, I computed this guy. Then I right multiply. The blue line shows the new term. You right multiply the result by the new term, or by a new term to get the new derivative. Then you right multiply that guy by a new term to get the next derivative. Then you right multiply that guy by a new term to get the next derivative. At each term, you keep right multiplying as you go way back. So as you go backwards through the layers, first you have to get the derivative for a z. You're going to get the right multiply the derivative for the y with respect to the Jacobian. Then to get the derivative with respect for the previous y, you're going to right multiply the derivative for the z by the weights matrix. And then off the side, the derivative for the bias for any layer is simply the derivative for the affine term for that layer. And the derivative for the weights for any layer is the product of the input to the layer and the derivative for the affine term of that layer. That's the entire backpropagation in vector format. And when you look at it this way, it's really very simple. And so the entire training algorithm for a neural network, when you write it in vector format, you're just going to do a simple forward pass, which we saw. Then you'd compute the divergence and the average divergence, the loss over the entire training. Actually, you'd compute the divergence for each training instance. Then you just do this little recursion going back, which is there in the pseudocode, to compute the derivatives for the weights and biases for every layer. And then finally, you average those derivatives. That's what this summation and division by t is doing. And this here is your gradient descent rule. It's the new update is going to be the current value minus some step size eta times the derivative. And so setting up the whole thing for, say, a problem like digit recognition, you'd be given data of this kind. Say if you're doing binary classification, you'd have instances of digits and labels telling you whether the instance belong to the class or not. If you were doing multi-class, you would actually have labels telling you which class each instance belonged to. And this is going to be converted to one-hot representations. And then on these data, you're going to just sort of go through the entire data. You're going to iteratively perform these updates. You'd initialize all your parameters. Then you'd iterate, where within each iteration, you go over all the data instances. For each data instance, you're going to pass it through the network, compute the output and the divergence, then go backwards through the network and compute all the derivatives. When you're done processing all the data, you compute the average derivative and subtract some step size or learning rate times that average derivative out of the current parameter values to get the new update. So just the story so far. Neural networks must be trained to minimize the average divergence between the output of the network and the desired output over a set of training instances. Minimization is performed using gradient descent. Gradients can be computed using backpropagation, which requires a forward pass of inference followed by a backward pass of gradient computation. And the computed gradients can be incorporated into gradient descent. So I'll stop here. I'll wait for 2 or 3 minutes. I've taken more than the promised 45 minutes. But if you have any questions, I will take them. Otherwise, these are the topics we'll address in the next class. Does this process really converge? How well does it learn? How will it generalize outside your training set? And what do these terms even mean? So any questions?